So, hello everyone. My name is Guillaume Queron, and I have the pleasure to be the chair for this tutorial session, which is going to be on neural operators. So we have the pleasure of having Kamiar Aziza Denesheli for this talk from NVIDIA. So you can ask questions on the Rocket chat, but otherwise there's going to be a live Q&A session. So in the middle of the talk at 10:30 and also at the end. So Kamiar, the floor is yours.
Okay, thanks, Kim. Well, thanks everyone for coming this early in the morning. For many of us who just made it here last night or even today in the morning. Okay, so today for this tutorial, we're going to talk about machine learning on function spaces, and this is about operator learning, which is a new field in or new paradigm in machine learning, which is concerned about learning maps between function spaces. And we'll talk about the importance of this field of machine learning and the first principles of operator learning, the emergence of neural operators, which are a generalization of neural networks to functional spaces, and we will finish this tutorial with a series of open problems. As you can imagine, it looks like a total new field of study, and we are dealing with many open problems, and we were going to talk about those. Before getting to the field of operator learning, let's have a quick and miles away overview of what we have done in deep learning so far. In deep learning, we have been concerned for many decades with domains such as computer vision, language, where the data is finite dimensional object. Okay, for example, the image is 64 by 64. Input and output is a label or sequence of words. So the input and output are finite dimensional objects, and data is finite dimensional. And we have made many choices in architecture design. We have developed a series of advanced architectures, from convolutional neural networks to UNets to transformers. All of these architectures, we have designed them with domain problems in mind, and in particular, these architectures are designed for problems specifically in computer vision and language models. Okay, and in all these problems, what we are concerned with is learning a function which maps a finite dimensional object to a finite dimensional object. Here, for example, we have a bunch of images, we have labels, and we have a training data set. We trained to map the input finite dimensional object to the output finite dimensional object. So along the way of our endeavor in deep learning, we have put so much effort in developing data sets for training these machine learning models. We have had MNIST, we have had ImageNet to many language models data sets like Common Crawl and many more. And the domain knowledge in these areas, specific in computer vision and language models, helped us to develop problem setups, define the problems, what are the supervisions, and what are the loss functions we need to use to train the model, what are the metrics to assess the problems. Okay, most of these developments we have had were for domains such as computer vision and language, and a few other that we have had, but mainly influenced by these domains. Okay, but we have made a series of great discoveries in the field, and have been able to tackle many of the real world problems. Okay, but if we just take one step back and go back to university and pick a university, and look at the many departments in our undergrad university. Not many of them are concerned with classifying images or basically pictures or language models. For example, in dermatology department, we care about the study of skin, which is like a tissue on the surface of the body, and we are analyzing that. In geophysics, we are interested in subsurface structure of the Earth, and we care about wave propagation there. In molecular dynamics, in biology, or in medicine, we care about like protein engineering, which are like the evolution of the molecules in time, which are the continuous function in time. Or in sustainability or climate modeling or climate mitigation, we care about like storing carbon dioxide, for example, in subsurface Earth. In in mechanical engineering department, we care about aerodynamics of cars, building airplanes, the fluid dynamics around these subjects. In climate modeling and weather forecast, we care about like the evolution of the air or atmosphere and ocean in the on the surface of the Earth. Okay, for all of these problems, if you look at it, the data is not an image, or the data is not a language, uh, basically like tokens. Here, the data, for example, for weather forecast is function defined on sphere. Okay, and look at all these departments in the school, and they are mainly working on these scientific computing problems and project that all to industry. Almost like big portion of not almost all of it, but big portion of industry is concerned with these types of domains that are like where the data is function. Okay, so let's take a few examples, and we can go more depth in what I mean by function here. So in weather forecast, or in climate modeling, or in ocean modeling, the domain is a function defined on a sphere, okay, and the data is also a function, okay. So at each time a step, if I'm doing weather forecast, the input is let's say temperature defined on the sphere, and wind velocity defined on the sphere, and the output is again like wind velocity, temperature, precipitation, all of these variables, which are functions defined in a sphere, for which I care about spatial and temporal derivatives of them, because the spatial temporal derivatives of these quantities or these functions have to follow the physics laws, and integration over them should give me some physical quantities like energy or many other quantities. In seismology, we are concerned with the structure of subsurface Earth, which is a function representing the velocity field of subsurface Earth. So it's a function in 3D. And what we care about is like when we have an earthquake or any shaking somewhere, we care about how the wave propagates in subsurface Earth. Okay, so which is another function in space and time. So it's a 3D and in space and 1D in time, and we care about the spatial and temporal derivatives of it, because it should follow like Helmholtz equation or wave propagation equations. Similarly, in material science, we press materials start deforming, which is a function representing the deformation of this object in space and time. And here on the left, each of these boxes that I'm showing here is not a grid point. Each of them is a partial differential equation domain that you need to solve deformation for it. In fusion, the plasma dynamics follows the laws of physics, which is again a function in time and a space. In ultrasound imaging, we have an extremely nonlinear dynamical systems that, or not dynamic, wave propagation system, where we inject a wave into the skin or into the body, and we look at the reverse of it. And given the propagation of this wave is a function in space and time, and what we want to do, we want to solve an inverse problem by having the observation on the surface of the body. We want to see what is happening under. Same with seismology. When we have wave propagation, given observation on the surface, we want to discover what is in subsurface. These examples continue to molecular dynamics. In molecular dynamics, we have atoms moving in time as a continuous function in time following Schrödinger equation, which are all continuous. In robotics, the movement of the joints, all of them are continuous function in time. So function data is everywhere. Also, we have the grand challenge of computational fluid dynamics is modeling the interaction of the fluid around some objects, for which, as you see, the fluid around an object moves in 3D and is a function in space and time, for which we care about the spatial temporal derivatives of it, such that we know that they actually obey the laws of fluid dynamics and Navier-Stokes. So for all of these things, we care about the data actually is a complex function as an input, and output is also a complex function. And this extends to many other settings in scientific computing, which I'm not going to go over. But one thing very important is in the past few slides, we visualized the function by show them as pictures, but it doesn't mean that those are pictures. These are not images. These are not 64 by 64 images. These are actually functions that we need to deal with. Okay, so in scientific computing, like we just went over a few examples, and we have seen there are like very important problems and very important like domains in science. And the question is how we have been dealing with this problem so far. We have seismology has been a field for a long time. CFD has been a field for a long time. How we have been dealing with these problems. So the way we usually deal with these problems, to solve these problems as domain experts, I'm not a domain expert, but like the way domain experts actually deal with this problem is first, the procedure as follows. First, we try to model this physical phenomena and use like basic principled physics and some equations like Schrödinger equations, Darcy, Maxwell, Navier-Stokes, or many other fluid dynamics equations. We try to model these problems, this phenomena, as using some of these equations, and then develop suitable solvers for these problems. Okay, for example, finite difference methods, finite volume methods, and many more solvers, and then we solve these problems at some certain resolution. Okay. So to see what exactly happens here, let's take a very simple example. Here I'm showing Darcy flow equation. Okay, so where f is a source function. Let's say f is fixed, and a is a diffusion coefficient. I give you a, and I ask you what u satisfies this equation. Okay, so in order to know, so basically the problem is I give you a, which is a function, and I ask you what u satisfies this equation, and the map from a to u we call a solution operator, which takes input function a and output the function u. Okay, the way we solve this using, let's say, finite difference method is like we represent both function a and u as a table of numbers, like a matrix, and use finite difference to compute the derivative, like value on the right hand side minus value on the left hand side divided by the length is going to give me a derivative, and I compute the derivative this way for many x points, and then I get many linear equations, and I build this system of linear equations and invert it to come up with u. So this is basically the way finite difference methods work. Okay, and as you can imagine, as I increase the resolution, the solution becomes better and better. Okay, that's basically the basic way it's been done. And as you can imagine, also as I increase the resolution, the computation complexity also goes high. Okay. So great. So this looks straightforward and very convenient way of solving this physics problems. Why we don't continue in this direction? There are multiple reasons. One of them is real world is not that simple. So I'm just showing few equations out of more than 1,000 equations we use to do weather forecast. Okay, so these are just partial differential equation, part of the weather forecast equation. Few of them I'm showing. There are many more, and there are many algebraic part to them. We often don't, let's say, model clouds or mountains. What we do, we model, parameterize the macro behavior using some parameterization or some tables, and then we solve those equations. Okay, so this parameterization causes error. And if you guys are familiar with expert machine back in the 70s, we have these rule-based machines. We kept adding rules, and this is and at some point we were like, there's too many rules that we could not conceive them. Similar to here, even after adding all these equations, the accuracy of the weather forecast models are not to that point that we are satisfied. Second thing is, if you want to solve real-world problems, we need to solve these problems at very high resolution. As you can imagine, for example, for climate modeling, if I want to resolve fine details, the computation complexity of these methods is like unfavorable. We can't afford them. Okay. So in general, there are many limitations with traditional methods. I'm not saying traditional methods are bad. These are like the traditional methods have some limitations, and we're going to talk about how to complement them. So in traditional methods that we saw, someone needs to sit down and come up with this modeling of the equations, which usually should be human intuition friendly because the human is going to come up with those equations. and we need to spend many hours of study to come up with this, understand this unknown physics. The parameterization I said is a heuristic method and cause errors. Okay, and also there's this problem that so many of the solvers are not differentiable, and we need to solve some inverse problems. Then not having a differentiable solver makes the problem harder. As you might know, there are many efforts recently to make the solvers differentiable. There is another thing which is very important, is barrier to entry. Let's say I'm a chemist in lab and I want to come up with or I'm a livestock like epidemiologist, and I want to come up with a PDE to describe a phenomena I'm observing, and I might have too much on my plate to go and master the field of mathematics. Sometimes incorporating the domain knowledge, domain expert knowledge is quite hard. Let's say I say we need L1 error more than L2. Okay, and for that you need to make non-trivial changes in the solvers. When we deploy the solvers in real world, we observe data. It's not that easy to incorporate this data back to the solver. And also we talked about the massive computation complexity of these methods. Don't get me wrong, solvers are extremely data efficient. You come up with them, you just have like one person can write them down, so you don't need thousands of data or millions of data points to come up with the solver. You also, when you have a solver, you can solve them at any accuracy. So here, solvers are great, and when we want to accompany machine learning with these methods, they are basically going to be another tool in our toolbox. Okay, so given this limitation that we have, we hypothesize that machine learning can actually tackle these problems for us and make advancement in these areas. Okay, so in solver domain, given that function A, we had to solve for function U to come up with a solution to approximate that solution operator I talked about. In machine learning, we are like, hey, instead of solving for the output solution U, how about we predict the solution? Okay, so I give you a data set of A and U, which are functions. Each of these A and U are infinite dimensional object as opposed to finite dimensional object that we have had in neural network setting. And given the data, we are asking whether we can actually come up with a new machine learning paradigm which actually learns the map from input function to the output function. Okay, so regarding with respect to computation, we know that in last few years we have made a great progress in advancing the computational complexity of these solvers, and by incorporating like advanced algorithms, scaling them up, and using GPUs to speed up the solvers. But still, we need this additional speed up that the machine learning models would provide to us, which is like orders of magnitude faster than the best we can get for the solver-based method. So if you want to learn more, I would strongly encourage you to watch Anima and Kumar's TED Talk, which came out like a few days ago, on this subject, to see the importance of this operator learning and the future direction of the operator learning. Is highly recommended. Okay. Okay. Now let's talk about machine learning on function spaces. Okay. So in machine learning on function spaces, we have our data is basically pairs of input and output. Input is a function, output is a function. The first challenges that we are dealing with, we are facing in this area, is the fact that the input function and output function are given to us at some unknown, a priori unknown discretization or resolution. The input can be at some resolution, output can be some other resolution. Next data point, the input can be in totally weird mesh or discretization. The output can be like combination of regular grid and irregular grid. So if you're in the domain, if you have seen like core data in scientific computing, you know that many of the problems you have these types of irregularities, where the input function and output function, both of them are in different resolutions. Okay, and of course these grids I'm showing are like toyish grids. In practice, these grids are, or these meshes are very complicated and complex. Okay, so input and outputs are given to us at various resolution. We don't have control over it. Okay, and also the output that we want in operator learning needs to be a function. Okay, it needs to be a function because the spatial and temporal derivative or any derivative of it is going to be used to make sure that it obeys the laws of physics. And also we need to be able to do accurate integration over it to come up with some physical quantities, for example, like energy or the average temperature, or drag in the automotive industry is very important to compute, which is integration of the pressure on the surface of the car or plane. Okay. So in order to tackle the problems in operator learning, we have this new paradigm in machine learning called, or in deep learning, called neural operators, which are generalization of neural networks to function spaces. Okay, so to tackle these problems I brought up, we have this new domain in deep learning which does the job of mapping from function to function. Okay, so in neural networks, as we know, the input and output we talked about are finite dimensional objects. If you train your model on 64 by 64 image, and if you change the resolution to some other resolutions, the model no longer applies. But neural operators are designed such that they can apply to any discretization and resolution, and they are discretization convergent, meaning that the input can be given at any resolution, the output can be given at any resolution. The output of the model can be queried at any points, meaning that the output of the model should be a function. And more importantly, as we make the discretization finer and finer and finer, the model converges to a unique continuum. So these are the properties of neural operators. But before we define neural operators and what are these new generalization of deep neural networks, let's have a few slides about some basic topics that we learned many years ago, maybe some in high school, some in undergrad. One of them is integration. If I give you a function A and I ask you, hey, integrate this function A in this area, and I give you the point evaluation of this function A at some points x1 to xn, you can write a Riemann sum integration of it, and this approximates this integration, right? So this is the way we learn how to compute the integration back in the day. And we also know that as we increase the discretization, make the grid finer, this approximation becomes more accurate. Okay, so this is one thing we need to know to define neural operators. The second thing we need to know is if I give you a function and a value at like 2 points or 3 points, you can use finite difference to compute the derivatives of it. Okay, so these are the two prereq we need to define neural operators. Okay, so one of them was, in order to compute integration, we can use Riemann sum, which is summation of the points multiplied by delta x, and the derivatives can be computed using finite difference. Okay, so now we have this prereq established. We are ready to define neural operators, and we want to define neural operators by directly generalizing the formulation of neural networks. These next few slides are the most important part of the talk. If you get those, the rest of the talk is going to be straightforward. Okay, so let's look at the very basic neural network. Okay, and let's say the input to my neural network is this vector, which is a point evaluation of my my function and at this regular grid. Okay, so the first layer of my neural network, let's say its parameters like k, is going to be the linear model applied on this vector a, and summed up, divided by n, and then nonlinearity applied to it is going to give me the value at the next layer. So it's basically these are going to be activations at the next layer. Okay. So here I have oops. Okay. So this is going to be like my first layer of my neural network. So now let's go back to so here I have the AJ notation. Let's go back to the AXJ notation, which represent the value of the function A at point xj. Okay. So what I would get is going to be like a matrix multiplied by this vector of A's, which are point evaluation, is going to, and then after that I have nonlinearity, and then I get the activations at the next layer. So here I'm representing this matrix K indexed by I and J. I can also index it with, instead of I and J, I can index it with X, I, and Yj. sorry, x, j, and y, I. Okay, so I just took this matrix, which was like n by m, and represent it with a function, which can be a neural network or anything. I can just index it by, instead of I and j, I'm indexing it with x, j, and yi. Okay? And what else I'm going to do, I'm going to take this 1 over n, which was the grid size, and turn it to delta x. Okay? So basically, I can rewrite my neural network, first layer of my neural network, as this summation. Okay? Where instead of having this matrix K as my parameters, I have this function which represent the entries of this matrix. If you look at this very closely, what we see is this is actually the Riemannian sum approximation of this integration. Okay? So what I have in my neural network is actually Riemann sum approximation of this integration. Okay? And this integration is not on just A, is actually, sorry, A at these few points is on all a whole function A, okay? So this is basically, it's called linear integral operator in function spaces, which is basically a generalization of the linear model in finite dimensional spaces to linear model in infinite dimensional spaces, which is function spaces, okay? So we went from neural network layer, very basic neural network layer, to a linear integral operator layer. Okay? Any question? Okay, we will get to the question at the time. Okay, so this linear integral operator that we are having in function spaces should be very familiar to many of us, because this is exactly the same thing we see in impulse response in electrical engineering. Green's function appears in many equations, including wave equations. Frequency response and convolution, they have the exact same forms in, if you have done continuous time analysis and back in the day. And this linear integral operator that we have, which maps the input function A to the output function V, or nu, is also a solution to many, many basic PDEs. So this linear model that we have here is actually is everywhere in scientific computing and also in engineering. And it's basically direct generalization of linear model in finite dimensional spaces that we have been using forever to linear models in function spaces, okay? Okay, so let's look at this linear integral operator one more time. And as we said, in practice, the input function A is not given to us on a regular grid. It's like with the one we showed, it was like everything was equal to space, 1 over n. Usually is basically given us to some irregular grids, for which this integration, we can use Riemannian sum approximation to compute it. So any function you give me, A, at any discretization, I can apply this layer on it, and this is the way the computation is carried over. Okay, so this is basically a layer of neural operator, for which we have a function as an input, and the output is another function which we can query at any point we want. Okay, so the input is a function, output is a function. Input can be given to us at any discretization. Output can be queried at any point. Okay, so this is basically one layer of neural operator, a basic neural operator layer, which takes input as a function, apply linear model, and then similar to neural networks, we have nonlinearity. Okay, so in neural networks, as we all know, we have some basic components. One of them is bias. In neural operators, we are going to have, in neural networks, we have bias vector. In neural operators, we have bias function, because we need to query it at any point. And we have, in neural networks, we have residual connection almost all the time. Here, we're also going to have residual connection. And residual connection is a pointwise operator in neural operators. And it's very essential, because it allows us to basically easily approximate identity map from input to output function. And also, if you're concerned that this integration might smooth out your inputs, this residual connection would take care of that. Okay. Okay. For all of this talk, for simplicity, I am assuming that the input domain and output domain are same. But as you can imagine, this is not necessary, because this integration can happen, can map any function space to any function space. Okay. So In neural networks, again, to recap, we have linear function, which is like matrix vector product, and then we follow it with the nonlinearity and repeat it. In neural operators, we actually have exact same. We have, instead of having linear function, we have linear integral operator. We accompanied it with a nonlinearity, which is a pointwise operator, and repeat it to get a deep neural operator. And this is going to be the basic composition of a deep neural operator. So input is a function A, output is a function U. And this stacking that we have had does not violate the fact that I can output I can query the output function U at any point. Also, the fact that I have this composition does not violate the fact that I can give the function A at any discretization as an input to this model. So still the model after this composition is going to be a map between functional spaces. And the last and most important thing here is the fact that this architecture I just showed is a universal approximator of any operator. Okay, so any operator you give me, let's say the operator G dagger here is the operator I want to approximate. I have my neural operator, which is applied at some discretized version of A, input A. So the error between these two is going to have two components. One of them is going to be discretization error, which is like basically is inherent to the problem because input function A is given to me at some resolution or at some discretization, and we have approximation error. This one is controlled by the discretization, and for this one, which is approximation error, how well my operator can approximate the true operator, true solution operator in functional spaces follows this theorem. It says under some mild regularity conditions or assumptions, for any operator you consider, G dagger, and any epsilon you choose, there exists an operator, there should be G theta here. There exists an operator which approximate that the target operator with accuracy at better than epsilon. Okay, so this is basically you should not be worried about using neural operators for the lack of approximation theoretic limitations of them. They don't have that limitation. They can approximate any operator. This line of research of coming with approximation theoretic results for neural operators is very, very open, and there's need to be a ton of work in this area. So in conventional machine learning, when we do error analysis, often we are concerned with generalization error and approximation error. How many samples I have and how well my function class is going to approximate the solution. In neural operators, we have extra dimension, which is discretization. In conventional neural networks, the input is given to us, let's say 10-dimensional vector, that's the input. In operator learning, the input can be given to us at any resolution, and we always going to take into account that we are going to have discretization error. And here you also can see that precision comes to picture in a more relevant ways, because if you have discretization error, you might not need to carry your computation at very high resolution. Sorry, at very high precision. So you can actually have a trade-off between discretization and precision as well. Okay. Okay, now let's look at the full picture of a neural operator, basically architecture. The input to us, again, is a function which maps a domain D to a codomain RD. For example, in weather forecast, D is the capital D is the sphere, is like a 2D domain, or with the depth, if you wish. And the output of that function is RD, which is like many variables: temperature, wind velocity, I don't know, humidity, vorticity, precipitation, many things. And there are like more than 100 variables in weather forecast. So when the input function is like from this 2D domain to like 100 numbers, before we feed that function A to the basic layers of neural operators, usually we have a encoder layer, which is a pointwise operator, which takes these 100 numbers and map them to a feature representation. And also we have this decoder layer in the end, which maps the feature representation to the variables you care about. So these are like, we always have them. And this is going to be the full neural operator architecture in very simplistic case. Of course, we add many more components to the problem. Okay. So now how we implement this? one way to implement, as we spoke, is represent this K with a neural network. If we represent this K with a neural network, we can compute this integration using this Riemann sum, okay? And this integration can be either local or it can be global. And as you can see, this is semi-generalization of graph neural networks to to neural operators. This architecture is called graph neural operator, GNO, or sometimes kernel neural operator. And it's basically generalization of GNNs to this area. And the difference between GNNs is twofold. One of them is the fact that this model is discretization convergent, meaning that as I increase the resolution, as I increase the discretization, I would converge to unique operator. Another thing is like the graph that this model builds is with respect to metric space, not with respect to the graph itself. Okay. So that was one way, but you might ask, hey, what are the other ways to compute that integration? Integration has been there since like 300 BC. So there are gazillions of works on how to compute the integration. If I give you the input function, a function as some discretization, one way, which is very common, is take the input function, okay, and project it on a bunch of bases, multiply them by a bunch of numbers, or apply some neural networks or some function on those numbers, and project back to another function space. Okay, some function basis. So you take the input function, project it on like 10 bases. You take those numbers, manipulate them, mix them somehow, and then project them back using some other functions. Okay, and the projection, as you can imagine, is an integration of the base function with respect to the function we have, which we can carry it using the Riemannian sum integration, or any integration method that we know. And this is one way of doing integration. And as you might see, when I project the input function on a bunch of bases, I'm actually ignoring many pieces of information that exist in other bases that I'm not projecting. Okay. So, and now you see that the importance of the residual connection. Residual connection makes sure that you're not throwing away any information. Everything is going to be passed to next layer. Okay, good. So what if I choose this basis to be Fourier basis? We know Fourier bases are very much everywhere in PDEs, and specifically in fluid dynamics. And they are well behaved, they have great representation power, and blah, blah, blah. Also, we know that if I use the Fourier basis of my basis, I can actually resemble convolution. Okay, and if I represent my integration with the basis as a Fourier basis, the way I can carry this integration is basically I take the input function, compute this Fourier transform, and take my kernel and compute its Fourier transform, and then multiply them in the Fourier domain, and then inverse Fourier. This would give me the integration, which is basically convolution. Okay, so since the use of Fourier basis has this property, you can say, hey, instead of learning kappa, which is my learnable parameter, and then to compute the Fourier basis, I can directly just learn the Fourier basis of kappa. So basically, instead of learning the kernel in spatial domain, I can learn a kernel in Fourier domain. And this one gives me an architecture called Fourier neural operator. Okay, so Fourier neural operator, instead of learning the kernel directly on the spatial domain, you can directly learn it in the Fourier domain. As you can see, this is a semi-generalization of convolutional neural networks with a large kernel size to operator learning. Okay, so these things I'm showing here, most of them you can connect them with existing architectures in neural networks. Okay. Very important point about FNO, Fourier neural operators, is when the grid is regular. So if I'm given a regular grid, this projection I was talking about can be carried as a discrete Fourier transform. And if I have a discrete Fourier transform computation, I can compute this, okay, I can approximate this integration using fast Fourier transform, FFT, which we all know that is very fast and allows me to train and test on any resolution, as long as the resolution is regular. But if the resolution is not regular, I need to compute the integration using Riemannian sum. Okay, now we can train, let's say, FNO on some resolution of the data, and then query that model on higher resolution. So here I think we trained the model on 64 by 64, and this is like 256 by 256. So you can train the model on some resolution and generalize it, zero shot, generalize it to much higher resolutions. Okay, FNO is because of its properties of using Fourier bases, and also the fact that it's fast, have been used in many applications that, or sorry, many domains that I will cover later. Okay. You can imagine instead of using Fourier bases, you can use other bases like wavelet bases. You can do PCA on your dataset and learn bases of your dataset. You can use Laplace bases. You can use many things. You can also use neural networks to learn. Okay. As I said, we have been doing integration forever, for like thousands of years. So you might ask, what are the ways to do this integration accurately? One of the ways is Gaussian quadrature, which says when you do integration, just don't multiply it by delta x, multiply it also by omega, which is a quadrature rule. You can use Galerkin method. I'm going to use, if you are from machine learning, I'm going to use some fancy names here, but I will show you what are those things in correspondence to what we have in current state of deep learning. Galerkin method says, like you need to look at like different resolution differently, and for predicting at any point, you can just look at the solution at high resolution for that point, which is very similar to Gaussian pyramid method that we have in neural networks. Multi-grid methods say, hey, if I want to predict the solution at one point, just look at detailed physics at that point and like less detailed physics in far away, and that's basically pyramid method and YOLO combined. There's another method called multiple method. In multiple method is basically unit generalization, unit way of doing things in operator learning, which says anything happens far from this location is going to have average effect. Okay, so now I'll just show the multiple neural operator architecture, which says, given the input function, just do local kernel integration and then project the input function to a smaller domain and keep doing it. And this basically recovers unit. So it's basically a generalization of unit to neural operators. And it's called multiple graph neural operator, this architecture. In general, if you want to have a U-shaped neural operator, the input function, you take the input function and learn an operator which maps that input function to another function which has a smaller domain. So as you go deeper, the domain size shrinks. Okay, so this is basically the way, like, we correspond some of the methods that we have had in applied mathematics, which are there are many methods to do integration, but you can sometimes want one-to-one correspondence between the developments we have made in deep learning and many architectures in deep learning we have found that are actually effective. Okay, so we talked about some of the deep learning models like pyramid methods or UNet, how to generalize them, or CNNs, how to generalize them to neural operators. How about transformers? So I'm just showing a simple transformer or attention mechanism layer. Here, each point here is a token, okay? And given its tokens, I have query, key, and value models which take these tokens and mix them. Okay, this is basically the attention mechanism. How we turn it to neural operators? Well, basically the same thing. I turn these summations to integration and make sure that I consider this delta x's. So this is a way we can actually turn a transformer which applies to is a neural network to a neural operator becomes a transformer neural operator. Okay, so this is basically the way you can go from. You can take the implementation of the transformers and turn them to neural operators. And one fun fact is, if the grid is regular, this delta x and this delta x, they just cancel out, and you basically get the same architectures. Basically, you can apply the exact existing transformer architectures to operator learning problems, having in mind that the moment the grid changes, you need to change the grid and bring the delta x's back. Okay. There are other ways to apply the transformers to so basically generalized transformers to neural operators, and one of them is my favorite, is basically considering what is the problem in practice. So in many PDs, and as one of those we have observed, we are dealing with couple PDs. Many PDs are used to describe the problem at hand. And one of the problems that is very common is climate modeling. So in climate modeling, there are many, many countries and institutions, they are running their own climate models. They use slightly different physics, and each of them stores some of the variables and toss out some other variables. So we have many, many data sets. Each data set has different variable counts. Some of them has 100 variables, some of them have like 200 variables, some of them have 5 variables. So the question is, can we come up with an architecture with generalized transformers to, or attention mechanism to a setting that we can deal with variable in size or variable number of functions. And one of them is basically we do attention mechanism on the codomain of a function. So if the function has like 100 variables, I treat each of the variable as a token. Remember, each variable is a function, so each token is an infinite dimensional object. And we can come up with an architecture which actually is able to deal with many, many variables and data sets that carry different variable counts. Okay, so using this transformer architectures, we can develop self-supervised learning methods. We can generalize to unseen functions. If there are functions that we have not seen in our data set, we can actually fine-tune those. And also, there's one important thing here is that in language, we have like token number, like position encoding we have, this is fixed. But here, there's no such a thing. So each variable needs to have its own position encoding learn, which is the variable ID. Okay. So to this point, we talked about some of the main components of the neural operators, which were this integration, residual connections, and biases. And the question is like, are we done, or do we need more? So one more components that recently we found out is, is the fact that in many problems, let's go back to the Darcy flow problem. Here, let's say I give you the A is fixed, okay? I give you U and I ask you what is F, okay? The map from U to F is basically you take the U, compute its derivative, and it outputs F, right? So the map from U to F is basically derivative. But if I just use the components we saw for develop for neural operators to this problem, basically use integration to do this job, integration is not that efficient to compute the derivative. I mean, you can do it, but it's not that efficient. So we actually need to put the derivatives in to neural operators. And the straightforward way of doing it is actually using our knowledge from, I don't know, 70s or 80s, that CNNs have been used a lot for edge detection, and they actually can compute the derivatives. And basically, if I give you a CNN, you can construct the differential operator. Okay, so of course we need to scale each of the values with the grid size to make them actual derivative. And you might say, hey, I don't care about derivative in x and y, I care about directional derivative. You can actually make all of these values to be any number. As long as the summation is equal to 0, you get a directional derivative. So you can now add a CNN block to your neural operator and make sure that your neural operator is able to compute derivatives. Just make sure that when you double the resolution, you need to double these coefficients. If you make the resolution 10 times bigger, you need to make this coefficient 10 times bigger, because you need to have a consistent architecture. Okay, so this is the way you actually recover the derivatives in neural operators. And for irregular grids, you do the GNN. Okay, so we added these new components to neural operators. So here we can have a 5 minutes pause and have questions if anyone has questions.
Okay, so there's only one mic. So if you'd like to ask questions, please raise your hand and I will bring you the mic. To get things started, I will ask the question from Rocket Chat, which is why is a Fourier neural operator a semi-generalization and not a full generalization of convolutions? Can you elaborate on that?
Yeah, sure. So as we remembered in FNO, we were saying you take the input function and map it to few bases. Okay, so we are actually using like low frequency components of the input. Okay, so if you use the low frequency components of the input, if you translate it back to the special domain, the kernel you get is going to be a large receptive field kernel. Okay, so because we are using just first few high frequency components in FNO, we only recover like very wide kernels in a special domain. So that's basically the main reason. Of course, you can use many more Fourier modes, but still, if I double the resolution, you're going to not be using all the Fourier modes. So that's basically the main reason.
Thank you for your talk. I have a very it's here. I have a very basic question, like how do you represent your input function and output function, like by parameters or something else?
These are discretized. Let's say in weather forecast, I have the weather in San Francisco, in Vienna, in I don't know, Stuttgart, or some many cities and towns and points on the space on the 2D sphere. So it's basically discrete evaluation of my function at many points.
But you said you can query different resolutions. That means if you have a very crude output, then how do you query the more finer grid?
Okay, the data is residing on some discretization, but this neural operator model that we have just developed here together can output the solution function at any point you want to query at. Those y's that we had at uy, you can basically query those the output function at any point you desire. So the model is able to output a function that you can query at any point. Your data set does not have the output function at all the points.
Okay, so your input A is the discretized data points.
A is discretized at some many grid points. U is also discretized at many grid points.
Okay, thank you so much.
Sure. Let's have one more, and we carry to the. And we are going to have another session later in the talk.
So just over here. So I was trying to understand the real motivation for actually moving to neural operators. So one thing is I understand you can basically train on multiple resolutions. Is that one? I suppose that's one reason why we want to do that. Are there any more reasons, any benefits, any more benefits for moving to neural operators?
Great point. So one of them, as you said, is the fact that we can apply it on any resolution. Another thing is like, as we increase the resolution, let's say Riemannian sum, as you increase the resolution, become finer, it becomes more accurate. So we want to have an architecture which does that. Third thing is we need universal approximation property. We need to know that if I increase the resolution and if I have data at that resolution, I'm going to get better and better. Okay. And the last thing is the fact that the output is a function is very important, because in physics, I need to make sure that my model obeys laws of physics. Okay, so if I am predicting the pressure and like velocity of air around a car in fluid dynamics, you can't just give that one to the car designer and say use it. They need to check whether it's correct or not. So they need to compute the derivatives in space and time. Otherwise, they're like, how are they gonna make sure that, I mean, solvers, you can make sure they're correct or not, but if you don't output the function, they can't query and make sure that the solution is correct. So they need to verify.
Gotcha. And one quick other thing, what is the loss function that you're using to train?
That's a great question. So in computer vision, in language, we developed over many years, we developed the loss functions. Each of these domains, these are not applications, right? Each of these domains that we are talking about in fluid dynamics of cars, you go to weather forecast. For each of these domains, we need to actually design actually, I'm going to literally talk about it. For each of these domains, so in traditional machine learning, I mean, conventional computer vision and language, we have developed algorithms, losses, metrics, you name it, our data sets. For each of these new domains that in the scientific computing we are going to deal with, we need to redo all of these things. We don't have the right loss function for seismology. Well, what loss function are you going to use? We need to develop it. Same thing 50 years ago in computer vision, we didn't know what loss is good. Now we know better. Same thing for all of these domains. For weather forecast, what are the metrics we're going to use? Like L2, L1, what you want. We need to develop all of this. All of these things are unknown at the moment.
Thank you so much.
Yeah, sure. Yeah, so we talked about literally, thanks for the question, and talked about this, to answer the question, we talked about this setting. And again, one important thing, these are not applications, these are like domains of machine learning. We need to invent and rewrite machine learning for each of these domains. So don't expect that plug and play of any existing computer vision method here is valid. You need to make sure that it's actually the right thing to do. So let's go over a few examples that we have developed the specific neural operators for scientific computing problems. One of them is for weather forecast. We have there's an architecture called ForecastNet, which is based on FNO, Fourier neural operators, which you train it on 40 years of past data and ask it to predict weather, to do the weather forecast for let's say tomorrow. Okay, and this model, one of the first things you should see, what happened? I don't know what's happening, but this is like 45,000 times faster than traditional methods, conventional methods, which is very important. And also along the same question has been asked, we can train this model using L2 loss on function spaces, and we can evaluate them on using some metrics that the domain experts have, like ACC and stuff, but we need to develop many, many more. And another thing I want to point out is like the energy efficiency of these models is like 25,000 times more efficient. For this specific problem, we can actually extend our understanding and architectures and develop a specific neural operator architecture for this problem. One of them that we have developed is called a spherical harmonic Fourier neural operator, which does convolution on sphere. So it uses spherical harmonic basis instead of plain Fourier basis for the convolution, and which is basically Fourier basis in longitude and Legendre polynomial for the latitude. And this model, because it's equivariant and like satisfies many is basically inspired by the problem. And these bases that I'm talking about here are the bases even the domain experts use for their solvers to come up with a weather forecast. It's very domain inspired, and you can use this model to do weather forecasts. And the fact that it's very, very fast allows us to do ensemble prediction. What does it mean is in weather forecasts, the problem has a ton of uncertainty, and the future is stochastic. Okay, and we can use these models to do many member ensemble forecasts to see the distribution of the weather tomorrow, and based on that, we can come up with a better understanding of the weather. So anything in this area is open. The accuracy of the models are not there. The metrics we don't know. How to scale them, scale these methods up. We are making progress. We are not there. So basically, anything related to machine learning you can think of is open in this area. In the seismology, again, as we spoke, input is a function defined on in 3D. An earthquake happens, and a wave propagates in this domain, and we have observation on the surface. And given the observation on the surface, we're asking what is inside the physical domain. Okay, so that basically allows us to do inversion in seismology and understand explore the subsurface structure of Earth. One important example here is the CCS, which is about climate mitigation. So one of the tools in climate mitigation we have is basically injecting carbon dioxide in subsurface Earth. Oops. Is injecting carbon dioxide in subsurface Earth, and here, I wish you would have run. Okay, and we have a bunch of wells, and we inject carbon dioxide with some rates into subsurface, and we are asking how much carbon dioxide we can store, and how large this domain, the plume size, which expand in subsurface to 200 kilometers, is going to expand. So this is a very important subject in climate mitigation. Is one of the main tools we have to tackle climate. Okay, this method that we are talking about is 700,000 times faster than traditional methods. So you can imagine you can run this method for many realizations subsurface, because the thing is we don't know exactly what is the structure of subsurface, so we need to run this solver, so this method for many realizations of subsurface to do uncertainty quantification and come up with a method for that the domain reservoir engineers can use for optimization. Another setting that I really like is the molecular dynamics. In molecular dynamics, we have atoms moving using basically models using Schrödinger equation, which are continuous function in time. Many traditional conventional machine learning approaches were like, hey, this is the evolution of my molecule, and let's, given the state of the molecule at time sub t, predict the future. But the nature of the problem is actually continuous function in time. So this evolution is continuous function in time. So we can actually develop neural operator methods to basically predict the whole continuous function in time. And this way, you can actually have almost infinite amount of supervision for two reasons. One of them is this: when you skip this big jump here, the intermediate steps, the supervision, you're skipping them. But here you can use all the steps in the solver for the supervision of your model. And also, you know that each time a step, you need to satisfy the Schrodinger equation. So this basically gives you an emulator. So the domain expert can actually use this model to verify whether this model is correct or not. There are many other problems in the area of machine learning that are about functions in time. One of them is in diffusion models. We go from noise to image through the continuous function. And you can imagine there is a way to distill this continuous function in time using neural operator, where we give a noise as an input and output the whole continuous function in time, and we use all the intermediate supervision to tune the model. So you can actually use neural operators even to distill the models that are designed for computer vision. Let me also talk about this. In this problem, you are dealing with fluid dynamics of air around a car. That a car is given to as a very complicated grid on 2D grid in 3D domain, for which you can actually build an architecture based on combination of multiple architectures. You apply GNO on this irregular grid and translate it to regular grid, and then you can apply fast methods like FNO on the regular grid and then decode back to regular grid. Sorry, irregular grid on the mesh. Okay. So the examples are plenty. I don't want to go over examples. It's a tutorial about like learning what are neural operators. So if you're interested in examples, there's a Nature paper. I'll put it in the end, and you can take a look at many of the examples in this area. So far in operator learning, we talked about how we can train the operator using just input or output data. Okay, but one thing which is very essential in operator learning, which is different from conventional neural networks, usual neural networks, is like in neural networks, the supervision usually is coming from data and of course domain experts. But in operator learning, the supervision can also come from physics. Okay, so I know the output should follow physics laws. Okay, if I know that, this is an amazing supervision, how we can actually incorporate physics supervision in our equation. Let's go back to the Darcy flow equation. In Darcy flow equation, I know that this equation should satisfy. So I give the input to my neural operator and look at the output. And then when I have the output, I put the output and input to this equation to see whether it satisfies or not. If it doesn't satisfy, I just turn the violation to a loss and further train this model. Okay? So basically I can use, if my model violates physics, I can use that violation to further tune my model. So this is actually it's called physics-informed neural operator. It's a Pinot principle. You can not only use data of like input and output, also you can use physics laws to further train the model. So here, I train the model on this resolution, which is 64 by 64, and test it on 256 by 256, and then fine tune it using physics. And this is a spectrum I get. It's a very interesting thing we observe. So the black one is the spectrum of the ground truth data. The blue one is FNO trained on 64 by 64 resolution of the data. And then the green one, which is exactly lands on the black one, is Pinot fine-tuned neural operator. So there's no data of high resolution that the neural operator model has seen. It's just fine-tuned using physics. This is a very important subject because this data is cheap to generate. This data is not cheap to generate. Okay? Or getting these types of physical data is cheap. This very high resolution ones are very, very expensive. So you can actually generate as many data as you want here and fine-tune model on higher physics. Okay? You can also train your model on one data set of Reynolds number as 100 and just use the physics to generalize it to other physics. This is also a very important subject. If you have data scarcity, you can use this method to advance your model. Very important subject in Pinot is inverse problem. When we do inverse problem, we have input function A, we pass it to an operator, and then we get a solution. So now, given the solution, I'm asking what was the input that corresponds to this output. I can run gradient descent. We have done this for many, many times. You just run gradient descent on A to minimize this stuff and say, hey, claim victory and say that A is a solution. But when you put that A to the equation, that might not be even a physical solution, okay? So Pinot allows you to minimize this one with this constraint. So meaning that your gradient descent is going to just only explore the physical quantities, not any random quantity, okay? So seems promising. At least I'm very excited about the direction of Pinot, but is extremely challenging. We don't know how to do Pinot by now. There are very initial results and initial ideas how to do Pinot, but we don't know yet how to correctly impose physics, even partial physics. We don't know how to preserve quantities. You say, hey, mass should be preserved or energy should be preserved. How efficiently we do it? We don't know. This whole thing is absolutely open. And there's one thing we know that theoretically we should be able to outperform like existing solvers because these solvers are a special case of this mathematically, but we don't know, we don't have a right method to do these types of analysis, okay? Another thing that is very important is uncertain quantification in scientific computing. Let's see where we learn uncertain quantification. Almost all of us learned uncertain quantification in physics class, okay? When you report a number in physics class, the instructor was like, hey, what is the error bar? So uncertain quantification, yes, in machine learning, conventional machine learning, we have written thousands of papers, millions of papers on uncertain quantification, but uncertain quantification is so essential in operator learning and scientific computing that we actually learn uncertain quantification in physics classes, okay? So we need to come up with methods to do uncertain quantification. There are very primitive works, like, okay, by primitive, I mean, there are some initial works. One of them is generalization of conformal prediction to function spaces, which says, hey, you not only predict the solution of your operator, also give us upper bound, lower bound, and make sure that the upper bound, lower bound is conformal. And so there are methods like that that are actually very interesting because, like, when you use your neural operator model for in automotive industry, given the geometry you predict, like pressure on the car, the first thing the domain expert asks is like, okay, what is uncertainty? Is like, you're giving me numbers, how certain you are about numbers. So having uncertain quantification in neural operators is essential, and this whole field is absolutely open. We have like there are very few works in this area, and this is very important subject. Anywhere you give a neural operator or any machine learning based machine to domain expert, they immediately ask you about uncertain quantification. Another very important subject, generative models. Generative models, we have developed them for many image-based data, or like for language-based data. For function-based data is quite open. So for an example, I'm going to show you how to generalize GANs to function spaces, but you can imagine there are many other, like you can generalize diffusions and many other methods to function spaces. So for GANs, I'm just going to show the Wasserstein-based GANs. So we have a generator which receives a multivariate Gaussian as input and generate an image, and we show that generated image, fake image, and also the true image to the discriminator and train the discriminator using Wasserstein loss. So Wasserstein loss is this one, which discriminates between the image, the fake image and the true image. And you need to make sure that the Lipschitz constant of this D is bounded. Okay, so this is basically the way we have been doing GAN in images. How we generalize GANs to function spaces, which is called generative adversarial neural operators, or GANO in short. Input to the generator here is a neural operator. Input is not a finite dimensional vector or multivariate Gaussian. Input is a Gaussian process. Output is a function. This discriminator is also a neural functional, which maps the function to a scalar. Okay, so you show function at any resolution, the true function, real function at any resolution to the model, And also you generate functions at any resolution. This is Gaussian process, right? You can generate A at any resolution your computation allows. You generate the U and show these two, and the model will be trained using Wasserstein loss. Okay, what is a Wasserstein loss in function spaces? So D needs to now have like a Lipschitz constant in function spaces less than, let's say, here 1. Okay, so the way you compute the Lipschitz constant of a functional in function spaces is using Fresher derivative, that, and then you compute the norm of it in dual space of your function. So you need to consider all of these things when you design or generalize a generative model in neural networks to function spaces. Okay. So in practice, how you implement this is like, I mean, I'm using a bunch of jargons here, but how you implement them in practice it means that when you give a U at any resolution to your model, let's say the resolution is, or discretization is regular, when you ask the norm of the derivative in function space should be less than 1, it means that it should be less than 1 divided by the root of the resolution. Okay, so this is basically you compute that thing, Fresher derivative norm of it in dual space in function spaces. So this is a way you can train it, and this way you can actually train the model using any resolution. So if you don't do this, if you have one data which has extremely high resolution and compute the derivative of this one using traditional method, that is going to kill all your model. Okay, so you need to consider the fact that if the data has high resolution, it's still one data point. It's not like many more data points. Okay. Okay, so you can train this model at some resolution and just generate data as high resolution. This is as usual we talked about. There are many recent works that actually showed how you can generalize diffusion models to functional spaces. This is very interesting because theoretically has many challenges, because for diffusion model you need to go from the data to the noise, and you need to prove that the reverse exists even in SD sense or in an ODE sense in functional spaces. So you can actually do that, but noisification here again is not multivariate Gaussian, it's actually a function. Okay. There are methods that generalize variational autoencoder to neural operators. There are methods that generalize normalizing flow to neural operators, and like flow matching to neural operators, and many more. Okay. One of them that I kind of interested about is this model, which maps Gaussian processes to processes on any arbitrary stochastic processes. So in this case, so we all know GP regression, and GP regression assumes that the data is having like Gaussian prior. But as we know in practice, none of the data we are dealing with has Gaussian prior. Okay, so the data has this type prior. So what you can do, you can train a neural operator at any discretization to learn a map from the Gaussian process to any stochastic process which learns the prior on the function spaces, and you can do function regression. Now, instead of having Gaussian prior in mind, you can do it for any resolution. Sorry, any function distribution. So this is very important. We are applying these types of method to many real-world data, because real-world data never has Gaussian distribution in function spaces, and we can do functional regression, which is also very important if you do data assimilation in weather forecast. Okay, so in next few slides, maybe 5 minutes, we'll talk about open problems. Okay, first thing, I think all of us should be convinced that almost everything in this area is open. Okay, it's just new field. We need to basically rewrite all of machine learning, this time for function spaces. Okay. Okay, so one of the main important thing, neural operator architectures, so do not compare neural operators and neural networks. Neural operators are for function spaces, neural networks are for finite dimensional spaces. We need to bring ideas from neural networks to this area and make the neural operator architectures more advanced. Also, sometimes we can take ideas from neural operators to neural networks, which has happened before, to improve neural networks. So the thing is, the architectures in neural operator realm are extremely primitive. We have spent like years, more than like many decades to come up with all these advanced architectures in neural networks. We need to do exact same thing for neural operators to make the architectures there to be very versatile, that we can use them for many problems at hand. Okay. We talked about integration for aggregation of the information. is it the only thing we can do? Like, we have developed many methods in neural networks, max pooling, many other average pooling, you name it, like plenty of methods for information aggregation. Is integration all we need? Of course not. Do I know what is the solution? No. We need to figure these things out. We talked about integration, bias, and residual connection, and the derivatives, but all the components we need. I don't know. We need to develop these things. These methods are sometimes hard to scale up because of the fact that they need to deal with many resolution and discretization. They are very hard to scale up. This is an absolutely open problem. Pinot, I think, is going to be the future of AI for science, and it's extremely hard to train. So getting Pinot done right is actually a very important subject that we need to study. Inverse problem forever has been done using MCMC methods. Now we are going away from those. So we need to actually develop the theory and practice of inverse problems from scratch, using having all these new tools that we are having. Theoretically, approximation theoretic results, expressivity of them, like what are the basic core deep learning theory of the neural operators is still unknown, and we need to discover. There are generalization to computer vision. People have looked at this problem of image. Instead of looking at image as 64 by 64 thing, you can actually think about it as a continuous function in 2D. You can think about videos as continuous function in 2D and time, which is more relevant. Time in videos is not like time, like discrete time is actually continuous function in time. I said uncertainty quantification, and one important thing in this area is active learning. I personally worked in active learning many years ago, and we have developed many active learning principles in conventional finite dimensional machine learning. But active learning in function spaces is absolutely essential for a very obvious reason. Doing any experiment takes millions of dollars. So you can't just expect data set be there, beautiful, and we can just go there and use it. So we need to develop many principles of active learning for data generation, because data generation is just very hard, no matter you do it in real world or you're doing a simulation. RL, reinforcement learning in function spaces, is another important subject. We control fluid flow, we control like air like tunnels, and we control climate. All of these problems are open problems in reinforcement learning and function spaces that we need to develop. What are the challenges I have personally faced, and we probably many of us would face when we are dealing with domain experts? Is sometimes, I mean, it's understandable. Domain experts are sometimes pessimistic about deep learning and machine learning in general, and so we need to talk to when we collaborate with the domain expert, we need to be like very conscientious about this thing, and explain things carefully. Another thing is, it should be here. Another thing is, almost all the time, initial machine learning model you use or you propose in collaboration with your colleagues is not going to perform better than the existing methods. So you should be considerate about that. We don't understand when we're working with domain experts, we don't understand their field. They also don't know much about our field, so we need to build the bridge to just, remove these types of gaps in communication. And also, a very important subject. One of the reasons that machine learning is here today is because we develop data sets that are ML in mind curated. So ImageNet was curated having ML in mind. Many domain experts, they don't generate data. They have been generating data for like 50 years or so, 100 years, but they didn't generate it having ML in mind. Okay, so the data is extremely biased, so we need to work it out and develop. For each of these domains that we talked about, we need to develop ML data sets with ML in mind. And one last thing is, okay, we said we together we need to actually write all of ML for functional spaces, from unsupervised learning, transfer learning, anomaly detection, adversarial robustness. All of these things are actually absolutely unknown and unanswered in this area. So I hope that we are on the right track to know that future of AI for science is, sorry, future of scientific computing is going to be AI for science. And hopefully we will have in mind that when we are developing models, we actually talk with domain experts to see what are their needs. We need to have neural operator models that can work on many discretization, because the data comes from many discretization. They should be outputting functions because we want to compute the derivatives in the space and time to see that they obey the laws of physics. And one of the things that we are enjoying a lot these days is the fact that, by us I mean the whole humanity, is the fact that these methods are giving us extreme speed up, which means that we are going to advance science with orders of magnitude faster pace than been done for like last few centuries. So this is very important. Okay, so there are resources if you are interested in taking a look at the codes in related to neural operators. I just put two of them here. One of them is called Neural Operator Library. Another one is NVIDIA's Modulus. There are many other code bases out there. I just didn't exhaust the list. Some of the papers I talked about that I did not refer to during talk are here. I will put all of these things online, and the list of images and pictures I took. And also thanks to all my colleagues and collaborators to help develop this direction. And I hope that we can continue all of it together for the future of AI for science. Thank you.
Well, thank you very much, Camilla, for this great talk. So it's great. We have a lot of time for questions. So I'm going to start with questions from the Rocket chat. So two interesting questions. So first one, is there any way to impose guardrails on neural operator functions? And also how to handle the cases where the value of function is not defined for a given input? And then a second question, given that there are different ways to calculate the integrals, is this something to be considered as a hyperparameter or needs a more careful treatment by a domain expert? Is the code I know actually a remedy for that, since it can fuse different possible solutions on the same task?
Yeah, great question. So the first one, when the value of, okay, how to guardrail the output of the model, there are multiple ways. One of them is like you can, let's say you know that the output of the model should never be negative. You just can put the ReLU in the end and make sure that all the time the output is positive. We have used, well, there are many ideas. One of them is like using barrier functions for the training. That also has been heavily used in this area. Another thing that is very interesting is that you can actually impose the shape of the output function by multiplying your output function with a base function. That's also a very interesting subject, that you can impose physics directly hard-coded in your, or barriers basically hard-coded in your model. For the setting that the inputs, that output is not defined for the input, yeah, that's another consideration we need to make sure that the model is always valid in the domain that the input is provided. The last question, can you repeat it one more time?
It was about the different ways to calculate the integrals, whether you need to consider that as a hyperparameter and search for different ways.
Great point. That's another thing. So in neural operators, we train the model, let's say at some resolution, and then test it on different resolutions, right? So when we train the model at some resolution, the model itself might not, okay, the model will generalize to a high resolution and the accuracy is the same almost all the time, but we don't know why. Exactly. So the thing is, the model can learn weird stuff. So the thing is, there are many ways to do integration, and one of the ways is basically doing this Gaussian quadrature, which is actually very much related to the discretization you're having your model trained. But when you increase the resolution, the quadrature rule that your model learned might not be the right ones. Okay, so your model might actually overfit to the resolution as well. This is a very important subject. So we can overfit to, so in operator learning, we can overfit to the data. We can also overfit to the resolution. That's another thing that we need to consider, which is not similar to conventional neural networks. So it's an open problem. We don't yet to know. We yet to know how to do the proper integration and impose the model to learn right integration weights while training a model. So it's all open.
So maybe I'll also ask a personal question here. Since you mentioned that you have a generalization question on training on one resolution and then evaluating at a higher resolution, why would this generalize better than a convolutional neural network where you just rescale the resolution and you just go back from the test resolution to the training resolution and then interpolate to get to the higher resolution?
Okay. So that's a great question. So basically, if you train on, so there are two things happening here. So the data, so let's say we are dealing with Navier-Stokes or weather forecast. The data from time step t to time step t+1, the data has all the frequencies in it or all the resolutions in it because Earth went from time step t to time step t+1 and Earth solved the problem in continuum, okay, in all the frequencies. We only have access to the lower resolution version of that data. It doesn't mean that the data is solved at lower resolution. The data is just given to us at lower resolution. But the evolution of the data contains these higher frequency components, okay? So when you train them, if you consider this input data and output data as a function, you implicitly impose this implicit bias that, hey, the thing you are outputting and inputting is function. So when you actually increase the resolution, the model learns to generalize to these high resolutions by just having this implicit bias in it. This is the first thing. The second thing is when the data has higher frequency components in it, okay, so the model actually compensates for those high frequency components despite the fact that those are not in the input. So if I provide you with high resolution data and then you downsample and give it to neural networks, you actually discard all of those. The second thing is basically the fact that almost always in practice, you're given data at different resolutions. So if I give you data set at like low and high resolution, what you would do is one thing is to bring all the high resolution data to low resolution and train your neural network on. And in the end, you're not also going to get a function output. So these are like limitations that you want to avoid when you're training a deep learning model for scientific computing problems.
Okay, thank you. So we're going to take some questions from the room. Okay. Prior of locality.
Thank you. So all the architectures you mentioned don't depend on the input discretization, but to some extent, the input discretization needs to be consistent with the input discretization at test time.
That's the thing. So not exactly. Okay, so the input discretization, output, the data discretization and inference time discretization can be different. I showed a bunch of examples that you can train the model at, let me see, I have it. You can train the model at low resolution and directly test the model at higher resolution. I mean, maybe this one is a good example. So here you train, let's say, FNO on this resolution 256 and just test it on all the resolutions. It just generalizes.
Okay, but I'm not talking just about the resolution, but suppose you have some sparse, irregular discretization.
Yes.
And at test time, you have a completely different discretization scheme.
Okay.
So, I mean, computing FFT or this wouldn't work, right?
Oh, FFT, forget about FFT.
Yeah.
FFT was
Okay.
applicable only when you had regular grid. If you don't have regular grid, the projection on the Fourier basis happens through the Riemann sum. There is one point in your question is, what if when I train this model, the discretization is extremely sparse? Let's say I have the input function at, for weather forecast. Let's say that I give you the input at 10 points and ask you what is the weather tomorrow. I mean, you can train a neural operator where you can't expect it to do anything useful. Nothing can do anything useful. It's just you provide a 10 extremely sparse point. So in order to get this models working, you need to provide enough supervision in the input for the model to do the job of the prediction. Yeah, but if the resolution is very low, it doesn't. Or also if the distribution of the discretization is bad. Let's say your data on Earth, like all the training data points, we have extremely dense grid in the United States. The rest of the world is extremely sparse. And inference time, you get extremely the high resolution in Australia, and you get like extremely like low resolution everywhere else. So it's not gonna work very well. So you're gonna have this discretization error causing you generalization problem. So the generalization we're talking about here is also among the discretization, which is kind of unique to the operator learning problems. It's not. We don't have this funny neural networks that we need to generalize to different discretization. But here we need to. And also these are all open problems. We don't know how to.
Okay, let me go back to the basic definition of FNO, right? When you apply a linear operator on your input function, run it through nonlinearity and stack it, right?
Yes.
How do you represent those linear operators? They need to be represented by some finite number of parameters to be able to learn it. But maybe I didn't get it, or did you speak about it?
Yeah. So let me see. It's here. So this was FNO architecture, right? So given input function, you do Fourier transform, and then come up with a Fourier basis, so Fourier coefficients, and do multiplication in Fourier domain and come back, right? But in practice, in practice, this function fa is given to me at some discretization. Let's say the discretization is regular. Then the summation I would get that this is basically when I do Fourier transform, I project the function a on a Fourier basis, right? So this integration, I can compute it using this summation, right? Or I can approximate it using this summation. Okay. If the discretization is not regular, I get delta x here, and I still can compute it using like any summation, basically irregular DFT methods. But if this discretization is regular, I can compute this one using FFT. So basically, let me rephrase it. I never compute this. I almost always approximate this. And the approximation is using this Riemann sum. When Riemannian sum can be computed just by summing here or using FFT. So given a discretization, I still compute all this projection, all this Fourier transforms in the discretized domain. But the important point is I'm not limited to a fixed discretization. I can double the resolution. I can make the resolution 10 times bigger. Still, the whole thing works. That's the whole point, that you should be able to input the function at any discretization, and the output is a function you can query at any point.
Okay, I'm going to go with questions from the chat. First one is there any domain that we really don't need to go operator learning because it seems it has applications and benefits in every existing tasks of ML?
Say it one more time. I didn't catch the first part.
Is there any domain where we don't need neural operator learning?
Yeah.
So I'm going to ask two sub-questions. Why don't we see operator learning in image recognition? Because images are functions as well. And do we need to have PD data for neural operators to be to express all their powers?
Okay, great question. So first of all, we don't need PDs or anything of these things for neural operators. As long as the input is a function, output is a function, we're good. For weather forecast, we don't have the PDs, like very, very complex things. It doesn't have the PD representation. So the last question, we don't need the data to be finite dimensional thing. And also, sorry, doesn't need to be PD. And also we saw it for diffusion models, you can actually, there's this DOD. But yeah, but generally you don't need to have like physics problem. You can just you don't need to represent the PD. Regarding the first part of the question, why we don't use it in images, actually we do. Like there are some groups that have very interesting works in these areas. So I haven't seen anyone doing the second one, but the fact that the neural operators output function, people have used them for zero-shot super resolution in images. So you can have your image super resolution problem, and the neural operator outputs it at all the resolution. You can query the image at any discretization or any resolution you want. So people have applied these methods for image super resolution. And I haven't seen anyone applying them on videos, but of course, it makes absolute sense to apply them on videos because like video is not a discrete time series. Video is a continuous function in time, and if you have a model which goes from time step t to time step t plus 1, from t plus 1 to t plus 2, you're actually losing a lot of information. So it's like, but if you output the whole function in continuous in time, you get consistency. And I haven't seen here, but I've seen people applying on images for super resolution. But I'm expecting more of these ideas from neural operators to be extended to images or pictures.
Okay, I think part of the question was, are there tasks for which it's not relevant to apply neural operators?
Yeah. There are plenty of tasks, like recommendations. I'm Amazon, I want to recommend like this pen to you or the other pen to you. I don't need neural operators there. It's just neural net. Literally, the input is like 1 million dimensional feature representation of me, and the output is like what action I need to take. Should I show this item to you or next item to you for recommendation system? I don't see any reason to use, at the moment, for the state of recommendation system, I don't see any reason to use them. There are many, like in Atari games, like if you're playing Atari or if you're playing AlphaGo, you don't need neural operators. Or for AlphaFold, which goes from sequence to shape, there's no continuous function involved. But if you're going to do molecular dynamics, which is a continuous function in time, yes, you sure you need it. But for many, many tasks, you don't need it. But for many scientific computing tasks, you need them.
Okay. And also, question was, could you tell more about the mathematical relationship between diffusion and Langevin dynamics and neural operators?
Okay, that's a great question. So the diffusion models and Langevin dynamics are algorithms, okay? But the neural operator is like basically a paradigm in terms of architecture, okay? So you can have, they are not mutually exclusive. You can use neural operators for diffusion process. You can use neural operator for Langevin dynamics. So Langevin dynamics that we have been using a lot in many years. All of them were like Langevin dynamics in finite dimensional spaces, but you can do Langevin dynamics in infinite dimensional spaces, as we do for inverse problem solvers. So if you're doing MCMC in infinite dimensional space and function spaces, you would run Langevin dynamics on function spaces to do inversion using neural operators. So in neural operator, you go from, let's say in seismology, you go from velocity structure of the Earth to the wave and the output, and you have waves observation. You want to see what is subsurface structure. This inversion is ill-defined. So you can't go from surface observation and come up with the exact subsurface structure. What you do, you run Langevin dynamics here on the inversion of the neural operator and come up with a distribution of the inverted velocity structure. So they're not like on par to be compared. You can use Langevin dynamics algorithms when you're doing ML in function spaces, same as diffusion.
Okay, any question from the room? Okay.
What if your input function has discontinuities? Does that cause problems?
100%. So if input function has discontinuity, or even worse, output function has discontinuity, this will cause many problems for the architectures I described. But what we need, okay, so that's a great question. It's an open problem, how you deal with it. And there are ways to deal with such problems. If you know the type of discontinuity in the input or the types of discontinuity you will be encountering in the output, you can actually come up with methods which solve the problem. I'm not too much concerned with the discontinuity in the input, but if you have discontinuity in output, asking a neural operator output layer to output a discontinuous function without having any domain knowledge or intuition from domain is very hard task. Let me say one thing. In neural operator, in all these architectures, we have been trying to impose domain knowledge to the architecture, and this actually has been very fruitful. For Navier-Stokes data I just showed, okay, in conventional machine learning, we need millions of data points to train the model. For the Navier-Stokes one I showed, we used 800 data points to train. For this car, automotive industry, real-world Volkswagen car, real data set is like 500. So if you use domain knowledge in your architecture development, you can come up with methods that are very efficient. For the setting that I have discontinuity, I would definitely put discontinuous functions as a basis for my output representation. Without that, I don't think you can have or you would have nightmare for training. It just doesn't, it's going to have a hard time.
Hi.
Yes.
Thank you for the talk, very interesting. My question is about input domains. So you mentioned obviously the Euclidean space, and you also mentioned the sphere. First question is, what other kinds of domains this has been tried on? And also, what if the input domain domain of the input function and domain of the output function are actually different. So for example, you mentioned residual connections that sort of map the identity, but there is no identity in this case. So what is sort of the logic that you follow there?
That's a great question. So the thing is, let me rephrase the question a little bit. There are many problems. Let's say even in this room, I tell you the temperature field on the walls and ask what is the temperature field inside this room. The input domain is a function is defined on 2D on 4 walls, and the output is defined in this 3D. So how we go from one domain to another domain? Let's say, let me find. Okay. Okay, this was the integral operator we have had. So in this one, so I'm computing this guy, right? Here in this formulation, the y and the x, they don't need to be in the same domain. This kernel can take, let's say x is 2D vector, y is 10D vector. Okay, so this layer can go from 2D to 10-dimensional space. Okay, so this layer there doesn't have any problem. Okay, so we can go from any domain to any domain using this integration. But you had a very important question or point in your question about the residual connection. So when you have a residual connection, for example here, so in UNO, in U-shaped neural operator, you take the input function, which is defined in this domain, and after one layer, you shrink the domain of the function. So as long as you have the homomorphism between these two domains, like from this is 0 to 1 and this is 0 to half, you have a bijective map between these two domains. You can still do the residual connection by, instead of having nu of y, you can have nu of inverse transform of the domain. That is done in UNO. But if you want to have residual connection going from like 2-dimension to 10-dimension, you need to define different maps. But still is doable. So you need to basically repeat things many times. And the residual connection that I showed, okay, by the way, all these architectures I showed the basic version of them. Let's find the residual connection. Where is it? Sorry, this laptop is dying. Anyway, so the residual connection was a pointwise operator, which was W applied on A of Y, right? So in W itself is a neural network by itself. When it's a neural network, you can also input the query point and the output to it. So you can have nu of like X and Y and any other things you want to query at that point. So this is a way you can make sure that you map your input using the residual connection to a new domain, which is totally different dimension. So you can make that W also dependent on your Y and also your X. But you need to keep it to be pointwise. That's the most important part.
Yeah. Thank you for the very inspiring talk. I have a question. You mentioned that domain experts can check if the physics of the model makes sense. I was gonna ask if you could elaborate on this a little bit more, how this would work. Is it basically like a validation set which is kept back, or how is that derived, or how is that done?
No, that's a very good question. Let me show you this. This actually has been done. So in climate modeling, when you so the climate evolution is very susceptible to the carbon dioxide saturation of the atmosphere. If you increase the saturation, something happens called tipping point, which is a sudden drastic change, sometimes irreversible behavior in the chaotic system. So for example, domain experts told us that as you increase the carbon dioxide level, at some point suddenly the cloud coverage on the atmosphere goes to 0 or very low number. So that's called tipping point. So one of the problems that we have to deal with in science is like predicting this tipping points like years in advance. So the way we do it is like we make the forecast in the future, using an architecture called RNO. It goes from time interval to time interval. And when we forecast, like, let's say 10 years in the future, we have the continuous function in time evolution of the climate, and we give that one to domain expert. Domain expert puts that solution into their equation to see whether it satisfies the equation or not. Okay, if it doesn't, we know that it's actually what's called a tipping point. Okay, so that's one setting you can do these things. But other settings, if you for the car setting, I'm outputting like the fluid dynamics around the car, right? This is a function describing the evolution of the fluid around the car. I know this should satisfy Navier-Stokes because the experts or domain experts, they use Navier-Stokes to solve this problem. So they can put this solution that I gave to them into the PDE and to see whether I satisfy the PDE. If I don't, okay, toss everything out. But if I do, you can trust it. So you can basically verify, domain experts can easily verify your solution using the physics. Another thing in molecular dynamics, one of the reasons I emphasize a lot on molecular dynamics is like in molecular dynamics, you output the time, like the continuous function in time. And this is very important for the domain experts, because domain experts don't care about the trajectory. They also care about all the forces, Schrodinger forces, which are like second derivative of this trajectory. So they can actually go and check whether the thing you actually predicted fulfills Schrodinger equation. If it doesn't, you did not have an emulator. We have a question here.
Hi, thank you for the very interesting talk. I wanted to ask you, are there any problems where neural operators are needed, but they tend not to work so well? And could you maybe tell us like why that might be the case?
So they are not needed,
No,
but
they are needed.
They are needed, but they don't work well.
Yeah,
there are plenty of problems that they don't work well. Like there are, okay, do you take any super advanced, even for computer vision? Okay, the neural operator architecture, they're nowhere close to being given accuracy as good as VITs. Okay, but you can turn the problem to function learning problems. So it means that but at the same time, we know that the whole space of neural network architectures are subset of neural operators, because if I fix the discretization of my neural operators, I recover the whole class of neural networks. So if I'm not performing good as opposed to neural network model, means that my architecture is still like very, very primitive, which is, we obviously see it all the time. So that's the thing we need to, like, in neural networks, we have like gazillions of architectures. In neural operators, we have like 20, 30 so far. It's a very, very new field, so we need to develop more, many more.
Okay, thank you. And maybe one last question. So you said that the field, or like the domain of uncertainty and quantification is underexplored. Like, do you know why that's the case?
Yeah, there are multiple reasons. One of them is like in machine learning, we have not thought that much about ML on function spaces in the last century, okay, since 1930s. We have not thought much about like uncertainty quantification. Okay, we have not thought much about machine learning on function spaces. So we have not developed many methods in these areas. Well, my computer died. The second thing is, which is kind of interesting, is the domain experts. You expect them to have many uncertainty quantification methods, but all of their uncertainty quantification methods they have are based on solvers, are not data related, and they also don't have. That's also a little bit controversial statement, but in many domain science problems, the solutions are not. They've never been good enough to study these settings. Okay, so that I can elaborate more. There are domains that people use metrics that you're like, wait, what? Why are you using this metric? And the metric is like, you just take the output of your model and make it worse, the metric gets better. So it's not that they didn't know. They know it, but it's like the solutions were so not good that they were not thinking about coming up with better things to do, like better metrics or evaluation metrics, because the solutions were like not good enough. So these are basically the reasons we don't have much of it. Yeah.
Hello. Thank you for your for talk. I have a questions about the graph neural operator.
Yes.
And in your talk, that I want to say the node, if the nodes are functions and the relation, the edges are relations, so can you do multiple functions predictions?
Multiple function what?
A prediction.
Prediction. Yeah. Okay. When I say input is a function, output is a function, I mean input is a function which has many. The code dimension of the function can be like 100, and output. The model outputs a function which constitutes many functions. So it's not from scalar function to scalar function. We go from a function has hundreds of variables to another function which has hundreds of variables. So you can think about going from 100 functions to 100 functions. So they actually can do it. And for many PDs, you actually need to do a lot of these types of things. For example, the input can be the here for a Darcy flow can be the diffusion coefficient, which is a function defined on 2D, and the boundary conditions, which is another function defined on 1D, and you are supposed to output the solution on 2D. So you can have many functions as an input. You can have many functions as an output.
Let's say that the node features maybe for the graph, each node features is a function, right?
Each node features
in the graph neural networks, we say each node we have a feature vector to represent the node.
So it's a vector, not a function.
Vector. It's a vector.
Yes.
And for this, if we want to use the graph neural operators, so each node will be a function.
No, each node is still as a vector. Mm-hmm. Okay. So you take the input function, which is given to you as some discretization, and you do graph neural operator. It outputs at for each point, it still gives you a vector. Mm-hmm. It doesn't give you each point doesn't give you a function, but that vector, that the output of this layer can be queried at any point. So it gives you a function in 2D, let's say. But the output of each node is still a vector.
Okay. Okay, thank you.
Yeah, sure.
Hey, I had a question about the kind of the beginning of the talk where we covered rule-based approaches. I was wondering if there's any way to do like hard constraint, like adding physics rules as hard constraints rather than fine-tuning using Pinot.
Yes, 100%. So one of the, let's say, let me give you an example. Let's say you know that your solution at point 0 is 0, okay? Like your output function, and you know u at point 0 is 0. One way to incorporate the physics into architecture is just multiply the output with a linear function, which is 0 at 0. Okay, so you can manipulate the output function to hard code physics. You can also, let's say you have a condition that you know, let's say for weather forecast, that SFNO architecture I showed, you want to make sure that the solution is equivalent to the rotation. So if you rotate the Earth, the solution also should rotate. Okay, so these are like things you can actually directly encode into the architecture by making sure that the convolution you do is circular. Okay, but if you're asking like how to encode like advanced physics conditions, all open problems. We don't know yet how to do those things. But we know a few things, but I mean, you can make sure that the output is divergence free. You can do these types of very simple partial physics enforcement, but imposing all sorts of physics are absolutely unknown. We don't know how to do this. And so these are actually the future of the field. We need to know these things, and we don't know. Great question.
Hi. You told us that there are some problems with the Pinos, and are they very sensitive to the architecture of the models you use, like the activation function, or how to encode the time, or how to compute the derivatives? And can you give some practical advice?
You're asking about Pinot principle, right?
Yes, right.
Yeah, so yeah, the choice of the activations are absolutely essential. And way of doing positional encoding is absolutely essential. So the thing is, you are outputting a function and you're expecting this derivative to fulfill like physics. And that's not an easy task. So the choice of so if you, let's say you don't do positional encoding the way we do it in transformers, we can't do anything. Like we can't recover any physics. Or if you use just ReLU without any positional encoding, we can't recover any physics. So it's very important to use very high, moderately high frequency positional encoding for the NLP, so for the positional encoding of the X and T. And also it's very important to use right activations. Also very important to try all the methods. So don't directly, for practical purposes, don't directly go after like using autograd to enforce physics. Use all the methods, use Fourier methods to get the physics somewhere, use finite difference method. So you can also apply the finite difference method on the output solution of the neural operator. Use those to advance the training, so the physics laws better, and gradually go to the autograd. Starting directly with autograd is very challenging. I strongly don't recommend that. Well, but at some point we need to get to the point that this should be doable.
Okay, I have a question. Let's assume we have multi-layer neural network, this operator neural network.
Right, and neural networks or neural operator?
Yeah. And the input xi, they are set with our data we have. And output xj, they are defined by the points we need, right? But how we defined x, so to say, xk in the intermediate layers? So if you think we can actually optimize them in the inference time to maximize precision, right?
Sure.
Or
so this is a slide that might be useful. So here the input, as you said, is given to me at this x1 to xn points. Okay? You with me?
Yeah.
I just don't see where. So, but after doing this this integral operator or this Riemannian sum, as you can see, this layer, this k, is a learnable parameter. Let's say it's a neural network, which receives j and yi as an input and does the summation. I can query this one at any yj I want, right?
Yeah.
So it's like, that's why we say the output is a function. I don't need to output the function on these grid points. I can output the function at any point I want. So that's the difference between neural networks and neural operators, that you map the input function to output function.
But what yi we choose for intermediate layers?
It's like there are for many reasons. One of them is like in practice, the data is not given to you at the fixed resolution. Like in car geometry setting, each solver gives you like one mesh might have like 100,000 grid points, another one might have 10 million, or there are settings that we are dealing with a billion points. So it's not your choice. The thing is, the data is given to, input data is given to as some discretization. The output is given a discretization. When you go from one data point to second data point, and from second one to third data point, you're dealing with different grids. In weather forecast, you have lat long grid, which is like very nice, cute. There's another data set. The data is like on Gaussian grid, which is very weird. Another one is on Hilpix grid. Another one is on reduced Gaussian grid. The input data discretization is not our choice. It's given to us. Okay, so that's the reason you need to query at many points. This is the first reason. The second reason is, like, as I said, you need to make sure that the physics is right. So meaning that the output needs to obey the physics laws. And for that, you need to compute spatial derivative of it, okay? And temporal derivative of it to see whether it matches the physics laws. The third thing is many quantities you care about in physics, in scientific computing and engineering, are basically integration of the output function. When I compute the pressure on the surface of the car, I need to compute the very accurate computation is required to compute the integration of the pressure on the surface of the car to compute the drag, how much my car is pushed back. Okay, so if I can't compute this integration accurately, I mean, drag computation is extremely sensitive, guys. It's extremely sensitive. You need to have really fine grid to compute it. So you need to make sure that the output is actually functioning such that you can query, so you can carry these computations accurately.
Over here.
I
So
see now.
I wanted to ask about how do we think about inductive biases on operators?
100% a great question. So
yeah, because of course, in the CNNs we have this thing like translation invariant activations and so on. Maybe we want equivariance. How do we think of these inductive biases for operators? Are there more even?
That's a great question. So let me answer this question in two ways. First of all, yeah. So you brought CNN and inductive biases there. We designed CNN with this inductive biases for computer vision tasks. Okay, you might not need that thing for other tasks. So for any domain in scientific computing we're dealing with, you might need different inductive biases. Again, for each domain in scientific computing, we need to treat it as computer vision and build ML and AI from scratch. One example is in a weather forecast. In weather forecast, sometimes you're like, hey, as I said, like you might want to have this translation invariance. Like you want to have, if you rotate or equivariance, you want to be able to have this similar to CNN that you should be a translation invariant. You want to be translation invariant only in this axis, because in this axis you don't want to. Like the North Pole is not connected to the South Pole, so you don't need this. You have to avoid that. But you want to have translation invariance sort of properties, inductive bias in your architecture for this direction. That's a thing that the SFNO does, a spherical Fourier neural operator does. There are many other settings that you have inductive biases of the other sorts. For example, in fluid dynamics of like Navier-Stokes, even solvers are written based on Fourier basis. Okay, so we use that inductive bias into architecture in FNO and use Fourier basis as the means of doing integration. Okay, so this one allows us to do a lot more, become extremely more data efficient. So for each domain, we need to come up with its own inductive biases. For seismology, it's totally different types of inductive biases you need to come up with, because you're solving Helmholtz equation. In ultrasound imaging, nonlinear Helmholtz equations, it's just all of them, they require their own specific type of inductive biases. So it's not like neural network to neural networks for each domain. Even for neural networks, so each domain we need to come up with specific inductive biases. The same for machine learning on function spaces.
Yeah, and one more thing also, can we think of doing a form of compression with these operators also? In some sense, are there any results saying that maybe we can kind of achieve some compressibility of the data by learning operators altogether?
You again brought a very good question, and this is extremely important, and is along with one of the questions that why we have not solved this problem earlier. The answer to your question is yes, and is one of the reasons that we think machine learning is the future of AI in conjunction with the traditional method. The reason is, let's say, let's look at the temperature of Earth, okay? Or like let's say, look at the upper atmosphere variables describing like the wind velocity, upper atmosphere, like that, 50 miles up. That function, in the solver, in order to use it, you need to discretize it very, very finely to solve for the weather forecast. But that function, if you look at it, it's just extremely smooth. You really don't need that discretization level to represent that function. And one of the winning point of the neural operator and operator learning and basically deep learning in this area is like, for computation, you definitely need to represent your function at very, very fine resolution or discretization. But for learning, let the machine learn. And if the function is extremely smooth, absolutely you don't need that high of a resolution to represent it. So the answer to your question is yes, and there are ideas, but we have not, like I haven't seen people deeply exploring this direction. And it's very valid, and there are so many applications, very important applications in these areas that we need to tackle in terms of compressing functional data. Yeah, that is just open.
Okay, we're gonna go for the last question before closing the session.
Yeah, one. Okay, sorry. Right.
Okay, yeah. Thanks a lot for the great overview. I have a question about actually this slide. That approximation there that we have with kappa as the function times a, and that when you developed this, we did not have the delta xj. That is like coming from the Riemannian approximation.
Yes.
And we use this as a way to get to like that integral form. But when we are implementing, do we look at mostly the summation part, right?
Yeah, when we implement this one.
Yeah, so we can learn kappa directly, or we can also use the Fourier way of.
There are two ways. So if you use Fourier method,
yeah,
you represent this kappa in Fourier space. Okay, you can definitely do that. The first architecture I showed was GNO, graph neural operator, or kernel neural operator. You learn this guy literally using 3-layered MLP.
And then in that case, the discontinuity that you talked about in the output, would that then be much more tractable?
If you have a discontinuity output?
Yes.
Still no. The thing is, even if you use MLP to represent this kappa, okay, MLPs are universal approximators of all the functions, so you should be able to represent that discontinuity. But I highly encourage to not only use MLP, but also sum this with 20 basis function, which are parameterized by like their shift and the length, the width, and give those also as like along with your MLP, also have those as an input, where the parameters of those can be also output of an MLP. This way, you can actually make sure that your model has the right basis to represent discontinuity.
And
yeah.
Okay, I will ask the other questions later. Thanks a lot.
Okay, sure.
Okay, thanks a lot, Camilla. If you have any more questions, you can ask Camilla directly. So yeah, this was a great tutorial. Thank you very much.
Thank you, everyone. Thank you.